All right, so we got to this point last time where we were able to come up with a reducible representation. It had kind of a funky 2 plus 4 cosine in it, but nonetheless, it is a reducible representation for the 2p salts, which were represented by these x, y, and z vectors on the oxygen atoms. So now we have to reduce it. And one way to reduce it is just to stare at this. And, you know, it's easy to see once you're given the answer that this is the answer, right? I mean, we got a g plus, a pi g, a u plus, and a pi u. So we can see, you know, 1 plus 2 plus 1 plus 2, that equals 6. 1 plus 2 cosine theta plus 1 plus 2 cosine theta is going to be 2 plus 4 cosine theta, etc. And we could, you know, check this. But finding it's a little difficult. And you can imagine if you had some atom where, I don't know, you had 6 ligands and you needed to find the p salts, this will get pretty bad, right? And you know, you'd be staring at it all day trying to figure this out by inspection. So, you know, we don't have to do things by inspection. We have the formula to reduce reducible representation. So don't forget this, right? This was back at the end of chapter 2. And we have this formula that the number of a given irreducible representation contained in a reducible representation is 1 over the order times the sum of the number of operations in the class times the character of the irreducible representation times the character of the reducible representation. That's all fine and well. The problem is, what is the order of our point group d infinity h? Well, it's 1 plus 2 plus infinity plus 1 plus 2 plus infinity. It's infinity. So this formula breaks down, and if you plug it in, you're going to get, you know, nonsense in this formula. So what do you do? And I should say all of this is sort of just for your information type of thing for homework. It's not going to be exam grade material because it will take you too long to do all this because these are more complicated problems. But, you know, I want you to be able to do it for the homework and be able to appreciate this right here. So here's the workaround. What you're going to do is you're going to set up the problem in a lower order group and actually then ascend up into symmetry, which usually you don't do. You're always descending into symmetry like we talked about in vibrational spectroscopy for problem solving there. But here you're going to actually ascend up because you're already in something that's very symmetric, right? You're in a linear point group. So you're going to ascend up. Usually it's easiest, or it is easiest to use C2V if you're in C infinity V, or to use D2H if you're in D infinity H. So I'll show you how this works with D2H. We're going to pull up the D infinity H, D2H correlation table. You can derive these or look these up online. And so we're going to solve this exact same problem, but pretend it's in D2H and then convert in to D infinity H. So now we have more classes of symmetry operations, but it's actually going to be a lot easier. We have 6 p orbitals represented by these 6 vectors. And so identity is going to get us a 6. C2Z, that's going to be a 180-degree rotation along the Z. So x1 is going to spin to negative x1, y1 is going to spin to negative y1. The z1s are going to stay the same, and x2 is going to be negative x2, y2 is going to be negative y2. So that gets you a negative 1, negative 1, 1, negative 1, negative 1, 1. Add those all up together, you get negative 2. Next, it goes C2y. C2y is going to be, where's C2y going to be? C2y is going to be right down the middle here, right? And so here we go. That's going to be a rotation 180 degrees through there. So what's going to happen there? Well, x1 is going to spin, actually that should say negative x2, but it doesn't really matter, okay? Because it's going to something else. It's going to contribute to 0. I've noticed I made a few typos like that throughout this area, but again, if you have questions about how something's transforming, you know, let me know. But y2 is going to spin around to y1 is going to spin around to y2. Y2 similarly is going to go to y1. x2 is going to spin around and go to a negative x1, right? So that should be a negative x1 there. But anyway, the only ones that are, and so nothing's going to stay the same here. Z1 got spun to Z2, and Z2 got spun to Z1. So they all change, and that's going to get you a 0, right? They all change into some other vector or a negative of some other vector. There's not going to be any ones or negative ones on the diagonal of your matrix, and so you're going to get 0. Inversion, same thing as before, actually, exact same thing as with d infinity dh. You know, let's do one of them here, top, front, left. That's going to go to back, right? So that's going to get x1 to negative x2. They all change into something else, so you get 0. xy, that's going to be something in the xy plane. So to draw that, remember, these are on the central atom, these mirror planes here. So that's going to be something like this, right? So that's going to take stuff on the left and put it over to the right. So y1 and y2 are going to interchange. x1 and x2 are going to interchange. z1 and z2 are going to interchange. They all interchange, and so that gets you 0. xz, very similar, except now you have the plane here, right? And so y1 is going to go to a negative. Things on top are going to go down. y1 is going to go to negative y1. y2 is going to go to negative y2. And then all the x and z vectors are going to stay the same. You add those all up together, you're going to get 2. And lastly, yz is very similar in this way. It just now your x's went to the negatives, right? The x's went to the negative here. Things in front go to back. And everything in the yz plane, those 4 vectors stays the same. Again, that gives you answer 2. So now you can go and you can use your formula. You can plug it in. This has a finite order, right? 1, 2, 3, 4, 5, 6, 7, 8. 1 over 8 in your formula, beginning of your formula. Plug it in. You're going to get AG, all this, okay? Then use the correlation table, and you can see, all right, I have an AG. I have an AG right here. That's going to get me a sigma G plus. I have a B2G and a B3G here. That's good for a pi G. I have a B1U and a B2U right there. That's not good for anything by itself. BU, the B1U is good for sigma U plus. And lastly, I have a B2U and a B3U, and that's good for a pi U. So that gets us the answer that we had before by inspection with difficulty. It was a difficult one with inspection. That gives you, that's how you can do, you know, really difficult problems in infinite point groups, in point groups with infinite order, is by ascending up in symmetry. So now we're ready to go back to our main problem at hand, which is, you know, constructing an MO diagram of CO2. We have the solves.